Morning, everybody. Today we're going to talk about inverse sine, cosine, and tangent functions. Okay, so when you see this symbol here, y, it looks like it says sine to the negative 1 power of x. That's the inverse sine, or the arc sine. Okay, and what that is if I have a sine curve like this, this red curve right here, the inverse is the reflection in the line y equals x of that. So it's this green right here. Now, remember what an inverse does. If you have two sets, okay, you got set A and you got set B, and a function takes A to B, then the inverse function takes B back to A. Okay, so that's what this does here. Now, if you look here at this graph, and if you graph inverse sine on your graphing calculator, you'll see it's not like sine, where sine, sine goes on forever in both directions. It just keeps going like this forever. And inverse sine actually starts and then stops. Okay, now why does that happen? Well, because remember, if I reflect this red curve, this sine curve, I'm going to get something that looks like this. And that's not a function. So in order for that to be a function, we have to cut this thing off before it overlaps on itself. Okay, so it stops just like that. Okay, so this goes from negative pi over 2 down here up to pi over 2 up here, and it starts out, and the domain is between negative 1 and positive 1. Okay, so what does that mean? So here I have my trig chart, and you'll notice that some of the areas here are shaded and some are not. So what that means, the shaded area is where you can take an inverse, okay? So for like sine, I can take an inverse in the first quadrant, and I can take an inverse in the fourth quadrant. But here's the thing. You'll notice I've got some values written over here, okay? Negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. If I arc sine one of these negative values over here, these are really going to be hard to see on this particular graph, but when I arc sine, I don't get these values here, I get these values over here. Okay, because if you look at sine, or the arc sine, it's in these two quadrants. It's in negative pi over 2 to 0 and 0 to pi over 2. Okay, so that's where you can arc sine this thing. So when I arc sine here, it takes me over to a negative. It does not give me these positives. Now cosine, it just goes from 0 to pi. And the same with tangent, secant, or cosecant. Secant goes, this is the same as cosine because secant and cosine are related. Okay, so let's see here. If I go arc sine of negative 1/2. Okay, so the arc sine of negative 1/2, I'm going to find that negative 1/2 on my chart. Now I don't want this one. I'm in the sine column because I'm using an arc sine. I don't want this one because that's not in the range there. I got to find it where it's in the shaded region, right here. Okay, negative 1/2, and I go over here. I don't want 11 pi over 6. I want negative pi over 6. So the answer to this is going to be negative pi over 6. Okay, now what happens if well, let's look at another one here. So if I want to arc sine square root of 2 over 2. Okay, that's pretty easy. I go find square root of 2 over 2 on my graph, which is be right here, and I go backwards, and I find that that is going to be pi over 4. The answer to an ArcSine or an ArcCosine or an ArcTangent or any of those functions is going to be an angle, okay, probably in radians. Okay, so what about something like this? ArcSine of 1/3. Well, ArcSine of 1/3, there's no 1/3 on here that I can use, so I'm going to have to use my graphing calculator for this. Make sure that your graphing calculator is in radians mode though, okay? So I'm going to go, my sine key is 2 buttons above my 7. My ArcSine is right above that, so I go second sine. It gives me the ArcSine, 1 divided by 3, and then close the parentheses. And you hit enter, and this is going to be approximately 0.3398 radians. Okay, so I'll give you a second to do this one on your own, and then you can go ahead and pause the video here and then jump back on and make sure you get the right answer. Okay, ArcSine of negative 1/4, I'm going to go second sine, negative, I can probably use 0.25, I can use 0.25, and I'm going to get, this is approximately negative 0.2527 radians. I would like to go out to 4 decimal places. Okay, moving right along. All right, here I've got the ArcSine of the sine of pi over 8. Okay, now, keep in mind, these two functions are inverses of each other. So a lot of times you'd think, oh, that's going to cancel out, okay? So I could just cancel those out, and what's left is my answer. And the answer to that with this kind of stuff is that's true sometimes. Okay, so for this first example, pi over 8. If I look at my chart here, okay, I want the sine of pi over 8. So I go back and I look at my graph here. Pi over 8 would be somewhere between 0 and pi over 6, okay? So if I take the sine of pi over 8, it's going to put me somewhere over here between 0 and 1/2. Now, when I ArcSine, remember I can only ArcSine if I'm in the shaded region here. So I am in the shaded region, so that would just take me right back to where I started at pi over 8. And so in this case, these two things cancel each other out, and the answer is just pi over 8. Okay, what about the ArcSine of the sine of 5 pi over 8? Well, let's go take a look again at our chart. Where would 5 pi over 8 be? Well, that would be somewhere between pi over 2 and 2 pi over 3. Okay, so it's going to be just a little bit below this line right here. So if I took the sine of 5 pi over 8, it's going to put me right here between 1 and the square root of 3 over 2. Okay, now here's the problem. When I ArcSine, I can't ArcSine here because it's not in the shaded region. So what do? Well, I have to find another value for this. Okay, it might even be easier to just look at this. Let's say I did the ArcSine of the sine of 2 pi over 3, because that's on the chart. Okay, so here I would take the sine of 2 pi over 3 would be square root of 3 over 2, so I would want ArcSine square root of 3 over 2. But I can't I can't do this one. I can't ArcSine this one. I got to go do this one. So that would take me back, and it would give me pi over 3. Okay, that was easy to do because that one was actually on the chart. But how do I do one like 5 pi over 8 where it's not on the chart? Okay, here's what I need to do. I'm going to use symmetry to solve this thing. So remember, sine looks like this. Okay, and here is pi over 2, or that's 1 right there, okay? And 5 pi over 8 is just going to be just a little bit right here, okay? So we're going to put 5 pi over 8 right there. Now, I can only arcsine if I'm on this part of the curve or if I'm over here, okay? So, I've got to find something where I'm in this purple range right here. So this is a line of symmetry right here. So all I have to do is go the same distance over here, because if I have 5 pi over 8, my answer is right there. Well, where am I going to get the same answer right there? That's going to be at 3 pi over 8. How did I get that? Well, if you think of this as 5 pi over 8, this is 4 pi over 8, I'm 1 pi over 8 to the right. So if I go 1 pi over 8 to the left, that's going to be 3 pi over 8. So these are not going to cancel in this case, and I'm going to get 3 pi over 8 for my answer. So I've got to use symmetry in order to do that. Okay, now cosine. Same deal, it works almost exactly the same with arc cosine. Okay, my cosine looks like this. My arc cosine is a reflection in the line y equals x, and it's limited as to where it can be because this is not, if I continue this on like this, that's not a function. So we cut it off, and it goes between 0 and pi, okay, which is why, when you look at the chart, cosine is shaded between 0 and pi, because that's where I can go backwards here. Okay. So let's arc cosine negative square root of 2 over 2. So I go find negative square root of 2 over 2. There's 1 here, and there's 1 here. I can't use this one because it's not in the shaded region. I've got to use this one. So it's going to take me right back here to 3 pi over 4. Okay, inverse tangent function. So the tangent looks, it has an asymptote here and an asymptote here at pi over 2 and negative pi over 2, and it goes like this, okay? So the arctangent is going to do the same thing, okay? And it's going to be bounded by pi over 2 on the top and negative pi over 2 on the bottom. So if I look at a trig chart, where can I arctangent? I can arctangent from 0 to pi over 2, and I can arctangent from, whoops, I didn't shade the top area here. This should be shaded right here. So, and so should this. Okay. So, I'm in the first and the fourth quadrants again. Hang on one second. Okay, so now what we're going to do is we're going to find the exact value of the arctangent of 1. So come over here, tangent column, find 1 in the shaded yellow region. Not this one, this one. Come over here, answer is pi over 4. So the arctangent of 1 is pi over 4. Okay? Find the exact value of the arctangent of negative square root of 3. Okay, so I go find negative square root of 3 in the tangent column, that's right here. Okay, I come over here, I don't want, there's negative square root of 3. I don't want this answer, I want that answer right there. So this is going to be negative pi over 3 is going to be the answer. Okay, so what's this formula here? D equals 24 times 1 minus the arc cosine of tangent I, tangent theta divided by pi. Okay, that formula is the formula that tells you how many hours of daylight there is at a particular location on the Earth on a particular day. So, we need to know a couple things. What's theta and what's I? Okay, let's start with theta first. Theta is basically your line of latitude. It's the angle formed from the equator to the center of the Earth to the point on the Earth that you're talking about. So if we were talking about Milwaukee, Oregon, okay, here's Milwaukee, Oregon on the globe. This angle would be about 46 degrees in degrees, about pi over 4 in radians, okay? Now this is going to be measured in radians for this, so if you have the answer in degrees, you got to convert it. But that's how you get latitude lines, is it's the angle from the equator to the center of the Earth to the location of that point on the Earth. Now, I is a little more complicated, okay? Whereas theta changes depending on where you are on the Earth, I changes based on what time of the year it is, okay? So I is the angle from the equator to the center of the Earth to the sun, which this angle changes depending on what day of the year it is, because obviously in the summertime you have longer days, right? In the wintertime you have shorter days. So this angle gets larger and smaller. So let's look at, find the number of hours of daylight in Seattle, Washington on July 4th, if it is known that the latitude of Seattle is 47 degrees, 36 minutes, 22 seconds, and that I is 22 degrees, 48 minutes on July 4th. Okay. So, the first thing that we need to do is we need to write down our formula. D equals 24 times, open parentheses, 1 minus the arc cosine of the tangent of I times the tangent of theta all over pi. Okay, so there's our formula. We just got to plug in I and theta. Okay, so the first thing we're going to do is we're going to convert these to decimals, degrees and decimals. So I, 22 degrees, 48 minutes, that's going to be equal to 22 plus 48 out of 60. Okay, so I get out my calculator and I go 22 plus open parentheses 48 divided by 60, close the parentheses, that's 22.8 degrees. Okay. Now, okay, so then we're going to take this thing and we're going to multiply it by pi over 180, because we got to convert this to radians. So 22.8 times pi divided by 180. Okay, so that's 0.3979 radians. This is going to go here. Now I got to calculate theta. Okay, so theta is 47 degrees, 36 minutes, 22 seconds. So this is going to be 47 plus 36 divided by 60 plus 22 divided by 3600. So that's going to come out to be 47.6061 repeating. So now we're going to multiply that by pi over 180 to convert it to radians. And we're going to get 0.8309. Okay, this is going to go here. So now we can figure this out. So the daylight is going to be 24 times 1 minus arc cosine of tangent of 0.3979 times tangent of 0.8309 divided by this part divided by pi. Okay, so here we go. So I'm going to do the inside first. I'm going to do tangent 0.3979, close the parentheses, times tangent 0.8309, close those parentheses. So this is 24 times 1 minus the arc cosine of 0.4604 divided by pi. Next thing I'm going to do is I'm going to arc cosine this. So arc cosine answer, and I get D is 24 times 1 minus 1.0923 over pi. So now I'll divide by pi. D is going to be 24 times 1 minus 0.3477. So 1 minus answer. D is going to be 24 times 0.6523. And now just times 24. And I get D equals 15.655 hours. And that's that. So on July 4th, Seattle's going to get 15.655 hours of sunlight per day. Okay, here we go. Got a nice little assignment here for you. Lesson 5.1. Okay, you got about 26 problems. And get a nice little calculate the time for Milwaukee, Oregon on this one. So it'll be interesting. You can compare how much more daylight does Seattle get to Milwaukee on July 4th, because you got the same eye down there. So good luck with that, and I'll see you next time.